And we're on. Okay. So, the problem with this topic is that it's hard. Even for those of us who are familiar with it, it's still hard because some problems that seem possibly quite easy, we can end up with the wrong answer anyway. So the first thing to say is, don't feel like an idiot if you find it hard, because it really is hard. It's not your fault. Okay, so what happens in this sort of topic is that you're told about a lot of stuff, and then you get these problems which have all these words, and you're supposed to figure out what to do. And while there's these wonderful tables that Naomi has put in your lecture notes of selecting and allocating, it doesn't actually cover every possibility of what possibly could happen in a counting situation. And what you need is ways of coping with situations that you've never seen before. And that's what I'm going to try and give you some advice on how to go about counting things. And those tables will be in there as well. But this is the advice I want to give. And it's not in the same order that you've been taught in the lectures, because I'm assuming you've seen it at least once. Okay? So sometimes the order that you see it in is not the best order for remembering it in. So I'm going to try and put it in a different order that might make more sense after you've seen it all. Okay. Right. So firstly, some advice for techniques of counting. So the first thing that you want to do when you are trying to count something is think about it clearly and have a particular order of how things were selected or allocated or ordered. Okay, so think of it in some sort of time order so that you have a way of dealing with that. So basically, in general, be systematic when you're thinking about it, but also time is usually helpful. This will all make sense when I do some examples. Okay, so for example, if you're there was one of the lecture note examples, which was there's 40 runners, and there's going to be 8 runners in the grand final, and you want to know what order they could come in when they cross the finish line, but the current world record holder is guaranteed a place in the final. So you can think about that in a particular order. We put the world record holder in, we choose 7 other people to go with them, and then we can put them in a correct order. And that's one way of organising the events that are happening to create that outcome. Okay? It's not the intended answer, but it does give an answer. Okay? So 2, if things do happen in order, or you have a whole lot of options that are chosen one at a time, you should be able to multiply the different numbers of options at each stage, and that should give you the answer. Okay, so there's a certain number of options at each stage. The total number of options should be just multiplying them together. As long as things you do at one stage doesn't change the answer in the next stage. As long as everything at the second stage is the same number, depending on the first. So each stage has a number of options, multiply to get the total. Okay? The third principle, some people call the sheep counting principle, which goes, if you want to count sheep, you can get down on your hands and knees and you can count their feet, and you can divide by 4, and that will tell you how many sheep there are. And what does that have to do with this? The point is that sometimes the quickest way to count something is to count everything more than once and just divide by how many times you counted everything. Okay, so sheep. Count everything more than once, and then divide to get the real answer. Okay, and so far we've got 3 principles. And the last principle that we want to work on is that you can always count something else and take it off. So if you're asked to count something, you can say, well, with this running example, you could say you want the world record holder to be in there. Why don't I just count all the ones where it's not in there and take them away from the total, and that should give me the answer. So, and you can always split it into different categories. So, count something you don't want and take it off. These are the big principles of constructing most of these formulas off the top of your head. There is one final thing, which is try and look at it in a different way. And that's really general advice, but it's one of the ways of describing how one of the answers in these things. So, now that's very vague. But the main thing of looking at it differently is if you're putting things in boxes, you might possibly try and think about that as labeling things instead. If you're trying to choose things from a group, you might try and think about it instead of doing it the other way around, as putting things in boxes. So it's possible to think about something upside down in a way and get the answer quicker that way. Or even... Or there are many ways of looking at things in a different way. Okay, that's really general advice, but what I wanted to give you is something that if you saw a problem that was written down on the page, you might have your allocating and collecting tables, but you still don't know what to do, and this is trying to help you know what to do. And the rest of it, of what I'm going to say, is probably mainly examples, just to show you how I think about them. Better put the page. I will put these on my website too, PDFs of what I've written here. So, okay. On top of that, there is actually one other thing. Use stuff you already know. So if you happen to know about the choose formula or the NPR formula, what you want to do is instead of just looking at it differently, look at it differently so that it's possible to use something else that you already do know. Okay? That sounds like it shouldn't need to be said, but you do need to say it. Okay? So, under the category of stuff you should already know are the two main and fundamental things about combinatorics, which is the study of counting. And one of them is permutations and the other one is choose, so combinations. And I'm going to start there, even though you actually construct those two formulas from the multiplication principle and the sheet principle. Those two formulas are created from there. It's important to just know them because that's the basics of how this works. So, we've got the fundamental. Okay, so to order a set of n things, the number of ways to do that is n factorial. So n exclamation mark, and hopefully you're aware that that's 1 times 2 times all the way up to times n. Okay? Now mathematicians say that 0 factorial is 1, just to make it all nice and pretty with the way the maths works. But in particular for this one, if you've got n things and you know how to order them, that's the number of ways. If I have 8 runners in my final, the number of ways I can come into the finish line is 8 factorial, because that's the number of ways of rearranging 8 things. All right? The reason why this works is because of this multiplication principle. For the person who comes in first, I just do it. Person who comes in first, there's 8 choices for that person. The next person, you've already chosen one, so there's 7 choices left, and you multiply them all together to get the answer. But even without that, you should be able to go straight to here. This is something, when I say should, it means please remember to do this first. Okay, so the other one is choosing R things out of n, where order doesn't matter. Okay, a number of ways. So some people write it like this, some people write it like this, some people write it like this, Some people write it like this. They're all symbols of the same thing. Calculators tend to write it like this. Okay? So if you've got a Texas Instruments graphics calculator, under the catalogue it's under NCR, if you search for N, if you want to actually know how to do it in your calculator. In a Casio graphics calculator, it's under the options probability, and in an ordinary scientific calculator, it should be on the front, on the button somewhere, shift something, should be that. And you actually type it in that order. You will type the N and then that button and then the R. Okay, and there is a formula for this. There are two formulas I like to use. There's this formula, which is the reason why it works. So you sort of go, on the bottom you've got 1 times 2 times all the way up to R, and then on top you've got N minus 1, all the way up to however many you need to get the same number as the number on the bottom. I'm not going to put the formula there. So I'll give an example of that in a second. And the final formula that uses factorials is n factorial on r factorial, n minus r factorial. That's the formal formula. This is the one that you would use in practice to do it by hand usually. So as an example, actually, I'll do an example on a different page. They're the fundamentals. So because most situations when you're counting things can be constructed from one or both of those things. So that's what I would recommend you just remember. Everything else you can turn into one of those situations or slightly separately to that. Something constructed from those. So while we're talking about these numbers, we actually need to know a few things about how the maths of those work so that when we get to a point where we have a formula, we can actually figure out what the answer is. So while we're on the topic, let's do the maths of choose. Okay. The maths of n factorial and n choose r. So with n factorial, those of us who are actually used to counting have a list in our heads of up to about 5 factorial that we just know off by heart because we keep using them all the time. But it's good to know that, say, 1 factorial is just 1, and technically 0 factorial is 1. That comes up in other formulas. So the number of ways to not order anything is 1 way. That's what it says. 2 factorial would be 1 times 2, which is 2. And 3 factorial would be 1 times 2 times 3, which is 6. And 4 factorial would be 1 times 2 times 3 times 4, which is 24. And so on. They get bigger every time, obviously. And it is useful mathematically to be able to do things like this, to be able to say that 4 factorial is the same as 4 times 3 factorial, because that's the 3 times 2 times 1, because that will help you cancel things out from fractions if you do them. And that works just as well with n in it as well, if you're doing it with a formula. N factorial is the same as n times n minus 1 factorial. And some other cool maths that goes on with that is if any one of you do Maths 1B, which you may or may not do, you might see this if you're doing Taylor series, and you can cancel them out because the top one is 1 times 2 times n, and the bottom one is 1 times 2 times n plus 1, so they cancel each other out. There's all sorts of really neat things you can do once you've got factorials to make your answer simpler. That's the maths. With the choose, okay, so we know, let's just run this through. Anything choose 0 is 1. If you've got a collection of n objects and you want to choose none of them, there's exactly one way to not choose any. And anything choose the same number is also 1. So if I've got 8 things and I want to choose all 8, there's exactly one way to do that. All right? Cool. And let's just do an example. 15 choose 3. According to this formula, if I wanted to figure that out by hand, I'd go the 3 on the bottom, I'd do that factorial, 1 times 2 times 3. And on the top, I'll go 15, 14, 13. And that will be the answer. I don't have to do all the multiple factorials to make it work. I just need to make sure that the same number of numbers here as there are on the bottom. And that will work out perfectly well to give you whatever the answer is. So don't like it, it's going to be a big number. whatever 5 times 7 times 13 is. Awful, but that's the answer. And that's how to calculate a choose if you're interested in it. Okay? Right. And there is one final thing that's really important to know. N choose R is the same as N choose N minus R. So for example, we know that 15 choose 3 will be the same as 15 choose 12. These two numbers add up to 15, so they have the same choose. Because choosing 3 is the same as not choosing 12. So choosing, you've got 15 and choosing 3 to keep is the same as choosing 12 to leave behind. So that's a useful thing to know, just for the maths of it. And one of the problems with mathematics is that most mathematicians are used to this sort of stuff because they've had years to get used to it, and we sometimes forget that students are not as used to it as we are. And we don't necessarily forget it, we just forget to tell the students that you need to really practice and get used to some of these maths things so that it makes your calculations a little quicker. Okay, now for some examples. So let's do that one that I was talking about. 40 runners. This one's from the lectures. 40 runners, 8 in the final race. World record holder must be in the final. How many orders can they come in at the end of the final race? So my thing that I didn't say on the other one is that all of these word problems have a whole lot of information in them, and it's usually a very good idea to do exactly what I did here and just write them down in sort of dot point form so that you strip away all of the grammar and leave behind the information that you've been given. So one way of doing this problem would be to think, well, let's just think about this. Our world record holder, which I'm going to call WRH, our world record holder is chosen first. It's put into the final 8. And then we need to choose 7 of the remaining 39 to complete the final 8. And then we need to figure out what order they go in. Then order these 8 runners. This is one possible way of answering this question. The reason I'm showing you this one is because it fits the most natural order of thinking about how the final race is constructed. Okay? So this is one solution. So we have the first runners put in final 8. There's only one way to do that. We choose 7 of the remaining 39, so 39 choose 7. And then we order them, and there's 8 factorial ways to order 8 people, and that's the answer. You would need to actually calculate what that was, but that's the answer. Okay? There is another way of thinking about this problem, and I don't want to confuse you by giving 2, but what I do want to say is that if you think of a different way of getting to the answer, and it's also correct, then it's correct, and you will get all the marks that you deserve because you have found a way of counting it that is correct. Okay? So another way of doing it, or we could say, well, let's count how many orderings there are in total, and then subtract all the ones that don't contain the world record holder, because that will leave behind the ones that do. So 40 runners, sorry, 8 chosen out of 40 in order, right, would give me, well, let's just think this through. There is actually a formula for this in your notes, but I can never remember it. So this is what I do. I go, well, there's 40 for the first guy, and then there's 39 because the first guy's already come first, so there's 39 people to choose to come second. And then there's 38 for the third guy, and there's 37 for the next, all the way down to, let's see, 33. 40, 33, 34, 35, 36, 37, 38, 39, 40. Yes, there's 8 of them. Okay, cool. That's how many there are ways to have 8 chosen out of 40 in order. Okay, that's a total number, whether they include the, so whether or not the world record holder is chosen or not. And if the world record holder is not chosen, there's 8 out of 39 in order. So that would be that. And so you just subtract them, because we've gone all the ones, whether it includes them or not, take away all the ones where he's not there, leaves the ones where he is. So therefore, the number where the world record holder is there is equal to whatever this answer is, minus whatever that answer is. If I had a calculator, I'd do it. But that's what you would do. So that subtraction rule is actually often quite useful, because this is probably quicker to calculate than that. But to be honest, if you have a calculator to do it for you, it will come out the same answer. Okay? Right. So that's supposed to empower you to say, I could never possibly think of that subtraction thing. That's okay, there's another way. All right? There's always more than one way. Well, almost always more than one way. Okay. Right. So all the other situations you've been given can be boiled down to basically choosing and or arranging. So I'm going to actually run through that table that Naomi has in the notes now. Oops, already did 3. And sort through that. Right, so first one, Naomi has a table which has, this is for choosing and arranging. I can't remember the exact form for the table, because I'm going to draw mine as a 2 by 2. So, in fact, I will look up the table because I need to see exactly what Naomi said. So there's 4 possible situations based on whether you want the outcomes to be in order, whether you care, and whether you're allowed to choose the same object more than once. Okay, so there's ordered and unordered, and there's repetition is okay, and repetition is not allowed. Okay, and we're going to have R out of n. Okay, R objects are chosen out of n objects. Sometimes we'll care what order they came in, sometimes we won't. Sometimes we're allowed to keep choosing the same object more than once, and sometimes we're not. And those 4 situations are all the situations in which you could choose objects out of a group. Okay, so let's do them. So unordered, here we go. Ordered and repetition is not okay. We've already done a situation like that. We have the 8 guys out of the 40 and they need to be in order. Okay, we've got a formula for that. So I'm going to give these labels. So just a second. Ordered and repetition is not okay. We've already got that situation. You've got n objects. So there's 2 possible ways of coping with this. You either choose the R objects out of the n, and then you put the R objects in order. That's one formula. Alternatively, there is this formula, which goes like this. Or finally, if you like, n times all the way down to, and there's r of these in total. Okay? They're all the same formula. If you do the maths, they work out to the same thing. This one is saying, this is how many ways to choose r things out of n, and then we put the r things in order. Okay? This one is saying, a way of thinking about this is to say, well, let's just put all n of them in order and just choose the first r that we care about, and then it doesn't matter what the rest of them are, so we just divide by the number of ways to arrange those. And this one is saying, well, there's n choices for the first one and n minus 1 for the second one, and so on. And this one is the most natural one based on the original counting rules that I told you. And this formula works out to that same answer. And this one is based on choosing and then arranging. And they all give you the same answer, but the one in your notes is this, and there is a notation for that. It's NPR. So you choose them and you permute them, P for permutation. Okay? I'm going to put that one in because that's the one that you would have been told. Okay? But in the end, if you can't remember that exact formula, there are at least 3 options for you to choose from. So whichever one pops into your head, use that. All right. So what about ordered and repetition is okay? Well, that one can only be done by thinking through this sort of process. There's R, the first and the second and the third, up to the rth one, and there's n choices for that one. And then, so you've chosen one out, but there's still one left behind because you're allowed to put as many in as you like. And there's n choices for the next one, and there's n, and then there's n choices for the last one. So that's n to the power of r. So that goes here. And I never remember that this is n to the power of r off the top of my head. I always do this because I don't like to remember more than one thing if I can get it from somewhere else. So, okay? And that's quite different. The difference between this and that is that since repetition is okay, you've always got n choices. But in this one, repetition is not okay, so the number keeps going down every time you choose another one. So that's the difference between them. Okay. Finally, we've got unordered. So unordered, where repetition is not okay, well, we've done that one. That's n choose r. That's the name of that number. Okay, you just choose r out of n and you don't care what order they go in. That's the formula for it. Unordered and repetition is okay. Whole different story. In fact, it's the hardest one in the whole of this counting area is that one. So I'm going to do that in just a second. And this is where we get to the bit where if you look at it in the right way, you'll be able to figure it out. Okay. Right. So let's look at this problem in the right way. I need a new page to look at it in the right way because I'll need space. And I'm sure Naomi said all of this as well, but sometimes it's nice to hear it differently or again. So we have unordered, except there's no D in that spot in unordered. And repetition is okay. So, let's see. So we have all these objects, okay, and we know which object is which. So object 1, object 2, object 3, object n. And we choose r of them, and it doesn't matter, we might choose 2 of the same one. Yep. We might choose a couple of each of them, and then we produce r objects afterwards. So these r objects aren't in any particular order. So what's important here? Well, the importance is which objects we put in, and they're allowed to be there multiple times, so how many of each object there is. So what we can actually think about it is saying, well, what we're really doing is we're really just care about how many of each object there are. So you can do it as a formula. x1 for the number of object number 1 that's there, x2 for the number of object number 2 that's there, and this has to add up to R objects in total. That's what you would have seen in the notes. That's one way of thinking about it. Okay? The other way is you just think about it completely upside down and think you've got n buckets, which are your objects. You've got these R objects. And instead of thinking about putting these here, think about putting these here. So I'm saying I've got R objects that I want, and I'm just going to put a sticky dot on all of these ones that I want. And so I'll just put 2 sticky dots on that one, and 1 sticky dot here, and 2 sticky dots there, and that one there. So you're sort of putting these R dots into these n buckets. So, or if you like, you can actually think of having your R dots being put into n buckets. You might have 2 in that one, and that sort of thing. Okay? This is saying that one of the formulas for putting things in buckets later is the same formula as what's going to happen here. But we still have not got a formula for how to look at this. We need to look at it in yet another way in order to actually find the formula. What we need to do is think, oh gosh. We need some sort of, you can think of it in terms of instructions. If we think of it this way, we can say, well, let's move to the first bucket, obviously in the first bucket, and then you'll put some dots in there, and then you'll move to the next bucket. And then if you don't put any dots, you'll just move to the next bucket. And if you don't put any dots, you'll move to the, and so on. And so what you would get is this combination of instructions for whether to put a new ball in this bucket or whether to move to the next bucket. So you could say, you know, there's 2 balls in the first bucket and now move to the next bucket. No balls in that one, so move straight to the next bucket. There is a ball in that one, and then I move to the next bucket, and something like that. Okay? So that is a list of instructions for how to put these balls into these buckets. And now we can finally do the problem, because we have a list of balls and arrows, and we just need to put them all in the right order. We know how many balls there are, and we know how many arrows there are, because the arrows tell us to move from one bucket to the next. So there must be total R balls, or sticky dots, or whatever, and n minus 1 arrows. And so the total number of objects that we have here the total number of objects in this list is n plus r plus n minus 1. Cool. And so we can put these in any order we like, because we can not put any in the first one, so we can start with an arrow. And so we really just need to choose which of these are going to be arrows and which of them are going to be balls. So out of those r plus n minus 1 total objects, we need to choose r of them to be balls. So that's the answer. That's the answer. R plus n minus 1, choose r. Which is the same as the answer of choosing which ones of them are arrows. So you could choose r plus n minus 1, choose n minus 1 if you like. And that's the answer. I really would like there to be another way of finding that out, but I can't think of it without drawing a giant tree diagram, like in probability, which is too hard to follow. So it is actually possible for small enough situations to just run through all the possibilities and count them. And sometimes that's the quickest way. But this formula is now a formula that we can use. And personally, I never remember this formula. What I remember is this picture. If I can remember that, oh, cool, what I need to do is do this picture with the arrows and the dots, or arrows and the balls, and then it helps me remember this formula. Because for me personally, formulas don't mean anything in my head, but a picture I can remember. So for unordered, it's the dots and the arrows. And that's the formula. Okay, so my way of remembering that is to remember how to turn it into something that I know how to cope with. And this is the reason it's the hardest one, is you have to look at it in 2 different perspectives until you can figure out what to do. So we started with choosing objects more than once to create a collection of R objects, and then we've changed it into actually treating the original objects as buckets and putting labels on them to decide how many of each of them we get, and then we turned it into a list, which is basically telling my robot how to produce the collection that we want. So that's 3 different perspectives. But it also tells us how to answer this question. So if you want to just raw numbers and say, I want to add together 6 numbers and I want them to add up to 10, and I care which number is which, I can answer that. It's this problem. Okay? So knowing that they all go together is a useful thing to know. Awesome. Let's do an example of that, hey? Let's find one. So, number of ways to choose 10 balls from a pile with yellow, red and blue. Okay? So the concept here is we're allowed to choose as many red or yellow and blue as we want. We can have 10 yellow if we want to. We can have all 10 red if we want to. Any combination of those things. This is one of these problems we're allowed to choose with replacement. Okay? So my thinking would always go, what I'm actually doing is I have 3 possible colours, yellow, red and blue, and I'm almost considering I'm painting the balls to begin with. This is my bucket of red, yellow and blue paint, and I'm going to chuck my balls into those paints, and then they will be the colour they're supposed to be. So I have 10 balls to chuck into those boxes. And so if I think it through, I need a ball, you know, it's going to be something like that. 1, 2, 3, 4, 5. That's a possible options for what I could do. Stick a ball in the yellow one, move to the red one, don't put any in that, and move to the blue one. Oh crap, there's too many. And then put all the rest of them in the last one. Okay? So we've got the number of ways is we've got 3 colours, and that's so 3 minus 1 arrows. We've got 10 balls, and we're going to choose 10 of them to be balls. 12 choose 10. And 12 choose 10 is too hard to calculate. It's probably much easier to do 12 choose 2. Because 12 choose 10 and 12 choose 2 are the same. So that's 12 times 11, 1 times 2. So the 2 on the bottom is 1 times 2, and I have the same number of them at the top but going down. So 66 ways. Hope that's right. Okay? For me, that's the only way I have of actually remembering what to do in that situation. You may have others, I really hope you do, but for me that's the quickest way of me remembering what to do. Okay, what if you had to choose at least one of each colour? Because in this case, see here I didn't choose any red ones because I got to the red bin and then I moved it over straight away. What if, you know, as above, but must have at least one of each colour. Right? Well, let's just think that through. So let's try and find a story for how to put this together in making this choice. So the story could be we could choose one of each colour first and then choose the rest of them. So choose one of each first and then choose the remaining 7. Yep. So one of each first. There's only one way to do that. There's only one way to do the first option, so that's the one of each colour. And now we've got 7 balls left to still put into 3 colours, and so it's that. Okay? So what we've done is we've turned it into the same problem, but starting a bit later. Times 8 over 1 times 2, which is 36. Okay? And that's what I mean by, right at the beginning, use stuff you already know. So what you want to do is you may want to be systematic and think about the time order of events, but try and set it up so that after you've done something, you know how to do the next bit. What I did here is I went, okay, I could put them all in first, and now I have a problem that's the same as that one, but with less balls. And so I've got the formula that I can use for that situation. That's the story I want to tell. I've got about 10 minutes, and I want to talk about allocating. So what we've already done is we've already said that some perspectives where you're choosing objects from a collection are the same as a perspective where you're putting objects into buckets. And so there's a whole separate story of things that you want to count, stories that go, take a whole lot of objects and put them in containers. And that's the allocating, which I'm going to find in your lecture notes to see what Naomi talked about there. And some of these are really not easy, because the only way to figure them out is to go down to a lower level. Here it is. That's the notes you have. I didn't bring a pencil sharpener, so my pencils are starting to run out. I might start writing in pen. Or not. Okay. All right. Where are we up to? Page 8. All right. So you have this table here, the number of ways to allocate R objects into N containers. And we've got whether the objects are distinct or identical or some combination of them, and whether you have to have some in there or allowed to have none. Okay? Right. That's actually, let's think that through, 1, 2, 3, 4, 5, 6 options, which is more than the other one. But technically most of these are found in that same process that I did before. You put some of them in and then you figure out what happens afterwards. I'm not going to cover them in particular. All right. I'll make this table at the end once I've talked about it. So, allocations. So with allocating, you have a collection of objects and you want to put them in groups. Okay? And you can actually think about this in terms of the unordered and ordered as well, if you like. If the groups have no particular order, or if the groups have a particular order, meaning they're distinct, or if the collection of objects have no particular order, they have no particular labels that distinguishes one from the other, or whether they're all whether they do. Okay? So these objects could be distinguishable, or all the same. And these could be distinct, or all not the same because they have different sizes, but you can't tell which one's which until you put something in them. Okay? So that's 4 options other than the empty, non-empty thing. We've already covered one of them. We've already covered the situation where we have n objects that we know which object is which, and n objects that we do not know which object is which until we put them in the containers, and then that tells us what colour they were. So our first example was that we have all same objects into distinct groups or distinct containers. Okay, so that's my situation. Was I had balls. Until I put them in the container with paint, I didn't know what colour they were. So until I did the allocation, they were the same. Okay? So an example of that is 10 balls, either red, yellow, or blue. And we can think of that as having, and the 10 balls go in there somewhere. Okay? So that's what's called allocating. I allocate things to groups. All right? Or you could have 10 people that you don't care which person is which, and you put them into roles in a job, and those sorts of things. And we already have a formula for that. So we have n objects. Okay, that's from above. Okay, right. So if you have all the same objects, and you put them into containers that you do not care about which container is which, then it's a different story entirely, and that's partitions, right? That's right, isn't it? Yeah, identical is partitions. Because you don't care what order they go in. Yeah. Okay. So same objects and same containers, or if you like, identical objects, identical containers. The containers, once you put stuff in them, you'll be able to tell which container is which because they might have different numbers of objects in them. But the objects themselves, you can't tell them apart. So it's almost as if here, I don't really care which colour gets how many balls. I just care about the actual numbers of balls that end up in the bins. Okay? And so all I really care about is splitting this 10 into 3 different groups. And I don't care what order the group's in, I just care what the possibilities are for the numbers that go together. That's called making a partition. Okay? And this is not easy to calculate because there's no formula for it. Because everything's the same as everything else, there's no real way of talking through the order that you do it in because you can't, there's no order. So it's too hard. So what you need to do is you need to start, it's too hard, right? So the big difference with partitions is whether you want to have exactly 3 groups or whether you just want to have up to 3 groups. So that's the other issue, right? Because whether you want 1 in every group or whether some of them are allowed to have none. Yeah. Because partitions, there has to be 1 in every group. Yeah. So partitions in particular is that there has to be 1 in every container. Okay? This situation, I actually didn't care if there were any blues at all. So that's slightly different to this. Well, it is hard. I told you it was hard. It's not your fault. Okay? So the only way to do this is to think through your story and work your way down until you find something that you do know how to calculate. So we do an example of that. Split 10 into 3 groups. Okay? That's easy to say. Okay, 3 groups, don't care which group is which, they're in no particular order. I have to have exactly 3 groups, so there must be 1 in every group. All right, there's a notation for this. It's called partition 10 into 3. All right. Well, there has to be 1 in every group, so I'll just put 1 in every group to start with and see what happens after that. So here's my story. So first, put 1 in every group, yeah? And now there's 7 left to place, yeah? Awesome. Now that there's 7 left to place, damn, I don't have to put any more in any of the other groups. So I should really now decide how many groups there's going to be now. So decide how many get any more. Yep. So I might decide all 3 of them get another one, or I might decide just 2 of them get another one, or just 1 of them gets all the rest of them. So once I've done that, and now I say, well, these ones are the ones that get extras. Now I'm going to partition 7 into that many groups. That's what's left. So we've got possibilities. So there's 1 more that gets some, or there's 2 that get some more, or there's 3 that get some more. And now we're partitioning 7 into 1 piece. We're partitioning 7 into 2 pieces. We're partitioning 7 into 3 pieces. And then we're going to do the same thing again. Well, there's only one way of putting all 7 of them into 1 bucket, so that's awesome. And in this one, I could decide whether to put them in the same one or whether to put them in different ones. And so I could do it again, and I could do it again, and I could do it again until I figure it out. There's actually a formula for doing this. You sort of, since you don't know which one is which, you could put 1 in here and 6 in here, or 2 in here and 5 in here, and 3 in here and 4 in here, and then you're up to 4 and 3, and you've done that one already. So there's 3. The formula for this, the floor of 7 on 2. Okay? So 7 on 2 is 3.5, and the floor says I have to round it down. But you can just think it through. You don't have to have the formula. You can just say, all right, 1 and 6, 2, and figure it out. And this one, now it's too hard. What we're going to have to do is split it up again. So put 1 in every group. Decide how many get more. So 1 might get more, 2 might get more, or 3 might get more. And now we've only got 4 left. So we've got partition the 4 ones into 1 bin, partition 4 into 2 bins, partition 4 into 3 bins. And we can keep going until we actually are able to figure it out. So this one is 1, this one is 2. Yep. And this one, it's still too hard. So we'll do it again. And so we'll have 1, 2, or 3. And there's only 1 ball left, right? After you put 1 in every one. So actually, once you put 1 in every one, there's only 1 ball left to place. So there's only really one way of doing it because none of the containers are different from each other. So it's actually just... And we already know putting 4 into 3, the only way to do that is to put them all in and then put 1 in the other one. So there's only one way, right? One way. So the total number of ways we have so far is 1 plus 2 plus 1 plus 3 plus 1. So 1, 2, 3, 4, 5, 6, 7, 8. Now I'm sure there's a better way of writing that down in the exam so that Naomi knows what the hell you're talking about. But do this on your scrap paper and then do it nicely. Okay? I'm sure she'll believe you and give you at least some marks for writing that. At least 1 for getting the right answer in the end. Okay? But that's the only way to do partitions, and that's pretty much as far as I can go. The rest of the table you already have, and that's the best table you can do. But if you're allowed to have none, that's okay. Just choose how many of them have some in them and do the partitions from there. So the only step is that you don't start with this, you just start here. Okay? You start at this point where you decide how many get more than 1. There you go. Next year's team might get a better description from me. This was my first go of doing one of these for Maths for IT. So thank you for participating. And good luck with your exam. And you can come to the Maths Learning Centre and, of course, Naomi's consulting times too between now and the exam. The Maths Learning Centre is open all the way till the end of exams. I don't know when your exam is. So there. I'm not allowed to know, actually, as a lecturer.